Picture a scatter of dots on a chart, house sizes running along the bottom and prices climbing up the side. Your job is to draw one straight line that captures the trend as tightly as possible. That single line is linear regression, the oldest and simplest predictive model there is, and almost everything fancier in machine learning is really just an elaboration of it. Master this one clean idea, and a huge chunk of the field suddenly clicks into place. So how does a machine decide which line, out of the infinitely many it could draw, is genuinely the best one? Let's break it down. At its heart, linear regression is a tiny pipeline that turns your inputs into a prediction, checks how wrong it was, and nudges itself to do better. Follow it one stage at a time. Start with your input features. These are the numbers you already know about each example, like square footage, the number of bedrooms, the age of the house. Every feature is a column of raw evidence the model is allowed to use when it makes a guess. Now multiply each feature by its own learned weight and add everything up, plus a baseline intercept. That weighted sum is the prediction. A big positive weight means that feature pushes the price up hard. A weight near zero means the feature barely matters at all. Here comes the moment of truth. Compare the predicted value against the actual value we already know for this training example, and measure the gap. We square that gap so misses in either direction count, and so that large errors get punished far more than small ones. Finally, adjust the weights to shrink that squared error, then repeat across all the data. Over many passes, the line settles into the fit that makes the total squared error as small as it can possibly be. That best fit is what we call the least squares solution. So why bother fitting a line at all instead of something simpler? Here's the contrast laid side by side. Suppose you just guessed the average price for every house, no matter its size. That baseline completely ignores the inputs. A tiny studio and a sprawling mansion get the exact same prediction, which is obviously useless the moment features actually carry information about the answer. You have thrown away every clue the data was handing you. Linear regression instead fits a line whose slope leans on the features. As square footage rises, the prediction rises with it, and each weight tells you precisely how much. That single tilt is what turns a lazy average into a genuine, input-aware forecast that adapts to every example you feed it. Strip everything away, and three ideas make linear regression what it is. The model is nothing but a weighted sum of the features plus an intercept. That is the whole formula. Its beautiful simplicity is exactly why it trains fast, runs anywhere, and stays easy to reason about. The weights are chosen to minimize the sum of squared errors. For small problems, there's a neat closed-form solution, the normal equations, and for large or wide data, we lean on gradient descent to find the same answer step by step. It is interpretable and the base for nearly everything else. Each weight is the effect of that feature holding the rest fixed, and logistic regression, ridge, lasso, even neural networks are all elaborations of this one core idea. Alright, let's lock in what matters. Linear regression fits a straight line or a hyperplane that predicts a continuous target as a weighted sum of the input features plus an intercept. Training means choosing the weights that minimize the sum of squared errors, solved in closed form for small problems and by gradient descent at scale. Its superpower is interpretability and speed, and it assumes a roughly linear relationship, so it struggles with curves, interactions, and outliers unless you help it along. Every heavier model you'll meet is really this idea stretched further. If you want the whole map of machine learning drawn this plainly, we're building exactly that over at standarity.com. Come learn with us.